Okay. So let me also today we'll finalize the previous topic about CPU scheduling and everything, including like non-preemptive scheduler and round robin schedule that we covered during our last lecture. You can expect in the midterm. I mean, additional information that we will cover today, like with respect to scheduling, that won't be in midterm, but whatever we covered last time, you should still expect it. So also we will look at some page table information, even though we covered this material in the past. I want to make sure that we kind of recap this information and we look at some examples. And in fact, I even moved project 2, some project 2 related information for the page tables to today, so that we can, that at least it can kind of also help you with the midterm preparation. So again, it's going to be relevant in that sense, even though project 2 is still going to be like, you know, after project 1 is due, right? So, but we'll look at the sum of this information because that's related to page tables. And hopefully that will be also useful for you. Okay. So last time we looked at the CPU schedules, and one thing that we looked at was FIFO scheduler. So that's a non-preemptive scheduler. But remember that with the FIFO scheduler, I mean, it may look fair, like first come, first served, right? But at the same time, imagine if you come to office hours and there is some student who takes all this office hours time, right? Even though the student came first, but other students, even they have short question, they are unable to ask that question. The same thing with tasks, right? If you have like really small task and it has to wait until some long task is finished, that is a problem, right? In terms of response time, because response time is really degrading for everyone else, right? On the other hand, it can be good if all tasks are short, you know, of all tasks are the same size, it can be good. But if tasks are very different, right? So especially like long task and short task, then it becomes really bad, right? So, and then you can even argue that it's not fair anymore, right? And the response time is bad and so on, right? So that was the non-preemptive scheduler, right? So then we looked at some, you know, other examples like short job first. It turned out that it's optimal for average waiting time, but unfortunately, or, you know, fortunately, we cannot predict the future. So, and therefore, you know, therefore it's not really practical in that sense. So finally, we looked at the preemption, right? And we, you know, we realized that we need preemption, and we specifically looked at the round robin algorithm, right? So we looked at the round robin algorithm and we defined the quantum. So in the quantum is a small period of time, like for us, in our maybe terms, like milliseconds, but in terms of operating system, that's like a lot of time, like ages, right? So, and if we switch tasks, we just give this quantum of time for one task, then switch to another task, then to another task, and so on. It turns out that we can have much better characteristics of the scheduler, like you know, better response time and so on, right? And if Q is large, if the quantum is large, then effectively we become again first come first served, right? It's going to be closer to FIFO, right? If Q is small, that can be better, right? So everything's kind of improving because we're given a small quantum for everyone, right? So everyone is processed. But at the same time, if Q is too small, then the overhead becomes too large, right? So therefore, we have to find the right balance between an overhead and between you know, so the performance doesn't degrade, right? So we have to find Q quantum size that is reasonable. So that is about round robin. So again, up to round robin, including like FIFO round robin, you know, all this you can expect in the midterm, right? So just a reminder, right? So make sure you understand these topics. So now let's look today at some other variations of the scheduling, such as proportional share schedulers. So this is just a generalization of round robin. A process is given some weight. So I think, I don't remember if it was this section or the other section. Somebody asked last time, like about priorities or so on, right? So for tasks. And so that we can also correlate with weights, right? So when we give a larger weight for a process, if it has a higher priority. So now, in addition to quantum, we have to kind of take into account weights for the process. So just as an example of a proportional, shear scheduler, you can consider lottery scheduling. Again, it's just an example, not such a big deal, but just to give you some idea. So you can create lottery tickets, which is equal, which would be equal of the sum of weights of all processes. So let's assume that the weight is an integer number. So the sum of weight is going to be an integer number. So you're going to draw a lottery ticket, and then you will decide which process to schedule based on that. So let's look at this example, right? So let's say we have process 1, and we assign certain tickets like 1, 2, 3, 4, 5, 6. Process 2, we assigned other tickets, right? 7 to 15. So process 1 has 6 tickets, and the weight is for process 1 is 6. Process 2 has 9 tickets, and the weight is 9, right? So now when we draw some lottery ticket, let's say we draw 9. So then we will have to, 9 belongs to process 2. So when we initialize, we decided, okay, this set of tickets belong to this process, another set of tickets belong to that process. So we draw 9, so like maybe random number generator what is a lottery ticket? It's just a random number generator, right? We draw 9, so 9 belongs to process 2, so you schedule P2 there, therefore, right? So then you draw 3, that belongs to process 1, you schedule process 1. So you draw 11, that's going to be P2. So, there is a high probability that you will draw more tickets, like we will schedule that process, there are more tickets, right? So therefore, this is correlates well with the weight, right? So as time goes by, process will get their share, right? So unless they are blocked, they should get their share. But it's only a probabilistic guarantee, right? So we cannot really say that it's for sure, but probably, unless your random number generator is bad, I guess you should have this correct distribution, right? Yeah, so it's just, again, just an example, not something that necessarily we have to use to actually implement it. Okay, go ahead.
Where do the weights come from? Like, does the CPU choose the weights for the processes?
No, we decide the weights of the process, right? Maybe we want to give a higher priority to one process than versus another process, right? So we're gonna give a higher weight for that process.
But where does that come from? Is it just?
Well, let's say it's come from the user or maybe operating system, right? So the user or operating system decides that this process is more important than the other process. So the CPU doesn't care, right? So CPU just schedules whatever you have, right? CPU just executes whatever you have. It's up to you to decide what kind of policies you choose. Okay, any questions? Okay. So there is another example of multi-level feedback queue. You can read the chapter 8 in OS 3 Easy Pieces. That's our main textbook. So it's up to you. It's not going to be required for any of the midterm or final exam or any project. So it's optional reading, right? So it's just, but again, there are some topics that are kind of optional. It doesn't mean that you shouldn't look at them, right? So if, just look at them, this can help you with, when you read some information that can help you with something else, right? Also. So the example of, this is a great example of heuristics that, try to combine conflicting goals of good response time and like fairness, right? Because you see there is also a problem of fairness and response time. It's unclear how to manage this stuff, right? So there is this is an old idea. You can look at this and but again, it's optional, right? Yeah, let's stop for scheduling here. Again, up to round robin, you can expect whatever we covered last time. Up to round robin, you can expect. So whatever lottery ticket I will not include, but just make sure you understand the basic stuff, right? Non-preemptive schedule, round robin scheduling for the midterm exam. Okay, so let me let's actually look at some sample exam question to kind of go through specifically one question. I think that will be useful for your midterm exam. Just give me 1 second. Yeah, so let's put it here. Sure, it's going to record well, but let's see. Okay. So one question that we have, and again, this is something we have looked in the past already, but I just want to make sure, and you also looked at the sample exam. I also want to make sure, because you may kind of get this question in the midterm, kind of a similar question in midterm, right? I just want to make sure you understand that, right? So the question is question 20, right? How many levels of page tables are necessary when using 2 kilobyte pages to support the translation of 29-bit virtual addresses to 32-bit physical addresses, assuming that each page table entry occupies 4 bytes? And then I'll also ask how to show how kind of arrive to that answer. Again, when you answer a similar question in midterm, right? I mean, don't put just an answer like 2 levels, right? So you want to show some steps how you write. At the very least, something that I kind of put here, right? But maybe even more than this, right? So just, but at the very least, so that I know that you didn't guess this answer, right? So you actually did some calculations. Yeah. So, okay, let's look at this example. So we have 2 kilobyte pages. So 2 kilobyte, how many, what is this number, 2 kilobytes? 2 to the power of what? 2 to the power of 11, right? Bytes. So again, just remember, I think I mentioned that in the past that certain numbers you have to just remember, like 2 to the power of 10 is 10,024, right? Oh, sorry, 1,024, right? To the power of 10, right? So it's easy to remember. And therefore 2048 is just to the power of 11, right? So it's twice as much. It's just really easy to remember this stuff. Again, this is something that people can even ask on the interview, right? So like they can say, what is 2 to the power of 24? Approximately, right? So remember, that's 2 to the power of 20 multiplied by 2 to the power of 4, so 2 to the power of 20 is approximately 1 million, because 2 to the power of 10 is 1024, right? 2 to the power of 20 is 1 million, 2 to the power of 4 is 16, so it's approximately 16 million, right? So you can easily answer that question if you just remember certain numbers, right? So yeah, no, I mean, I'm serious. Sometimes these questions can kind of come up during interviews, right? And again, right, so 2 to the power of 11 is 2048, right? So it's easier to remember these numbers. So 2 kilobytes, right? So this is the page size. This is the page size, right? Okay. So then the second thing that we worry about is the virtual address. I mean, we also have physical address, but physical address is maybe more to confuse you a little bit, right? So give you some extra information which is not relevant to solve this problem, right? So, but just to understand that you know what you are doing, right? So that we care about virtual address here. So the virtual address is 29 bits, right? So recall that you have 11 bits from 0 to 10. That is byte offset, right? 11 bits. Byte offset. And from 11 to 28, right? Because you start from 0. From 11 to 28, you have the virtual page number, right? VPN, right? So how many bits we have here? Virtual page number. 18. How many? 18, right? 18 bits. So this is because 29 minus 11 is 18, right? So we have 18 bits for the page number and 11 bits for the byte offset. So now, then the question is how many levels? Okay, go ahead.
I have a question here. So
Okay.
Since we haven't mentioned any kind of levels, how many levels, so do we by default consider 2 levels always?
Not necessarily, right? So it depends on the it's just how many levels. That assumes that it's a multi-level page table. So it can be 2, it can be 3, it can be 4, whatever. You have to calculate the number of levels. Doesn't make sense?
How do we come to know how many levels do we have to consider? For this, we have considered.
This is
2
the
levels.
question, right? So that's the question that we want to answer, right? How many levels, right? So that's the actual question that we want to be answering, right? So because we need to calculate what is the worst case scenario to map 29 bit virtual address, right? What is the worst case scenario that we have to accommodate? Like what is the and therefore we can calculate how many levels we have, right, for this worst case scenario. I mean, maybe even one level, right? So sometimes when I say how many levels doesn't even mean it. Maybe it's just one level sufficient, right? But you know, it typically implies that you know there are at least 2 levels or maybe more, right? So but the exact number we have to determine, right? It can be 2, it can be 3, it can be 4. That's that's what the question asks us, right? Okay, go ahead.
So basically, we couldn't split this any further, obviously, because we were to split 9. That would be like splitting bits. You can't do that. So this is like as far as we can go.
So where is not?
There's 2 levels, right?
Yeah. So I'll get to this. Let me get to this. So we first determined that we have 18-bit virtual page number, right? Okay.
Okay.
So then, in a multi-level page table. So the question is that it's how many levels, right? In a multi-level page table, remember the structure of the multi-level page table. You have level 1, that's the top level, right? That occupies one page, right? It points to another page, right? Level 2. I mean, of course, you can have more than this, right? So just show one example, right? That's also one page. Then level 2 points to level 3. Also one page, right? Then maybe level 3 points to level 4. And that is actually the final page, which has the leaf, let's say, and that's the leaf level. And that actually has the physical page number for the mapping. So all the preceding levels points to the physical address of this page, right? So the kind of like if you kind of turn it's like a tree, right? You have top level points to another level, and then finally that level is the where you have this mapping for the physical page number. So page table is like a tree, right? So that's only one page here. You know, maybe a lot of pages in the second level, even more on the third level, and even on the last level, we have the probably, I mean, unless we have some specific example, we have probably even more pages on the last level, right? So that is the idea, right? So the last level actually provides the mapping, the actual mapping. Previous level are pointing to the next level, right? So this root level points to the interior node, this is not interior node, this final points to leaf node, and the leaf node is actually points to the physical number, to the physical page number. So that is our idea, right? So with the multi-level page table. So we have to keep entries in the page. So we have to keep entries in the page. That means level 1 has to accommodate certain number of entries, right? Level 2 has to accommodate certain number of entries, and so on, right? So let's start with maybe level 1, right? So level 1 accommodates how many pages? So we have 2 kilobyte page size, and also we have the entry size. It's specified to be 4 bytes, right? So 2 to the power of 11 divided by 2 to the power of 2. So 2 to the power of 2 is 4. 2 to the power of 11 is the page size. That's going to be what? That's going to be number of entries, right? In each page. So it's going to be 2 to the power of 9, right? Or 512. It's also 512, but it's irrelevant, right? Let me just put 512 here also. 2 to the power of 9 entries that you have in each level. So it means in level 1, I have 2 to the power of 9 entries. In level 2, in each page of level 2, I have 2 to the power of 9 entries, and so on, right? So I have to translate 18 bits. So if 18 bits, okay, I have level 1, 2 to the power of 9. That's 512 entries. Points to level 2. Each of them is also 512 entries, right? This is 512, this is 512. How many in total I can have? 2 to the power of 9 multiplied by 2 to the power of 9. Or 2 to the power of 18, right? Entries that I can address with 2 levels. So so it turns out that we just need 2 levels because we have 18 bits here, and in each level we can fit like 9 bits, right? So therefore we just need 2 levels. Right? Does it make sense? Okay, go ahead.
So the exponent is what you're saying correlates to the bits in your virtual page number?
This one?
Mhm.
Yeah, so this is virtual page number, right? This is what we need to translate. So look at this also the question, right? To kind of confuse you, I also specify 32-bit physical address, right? Yeah, so physical address is completely irrelevant here because the only thing about physical address that is relevant here is that it has to fit in the entry size. And the 32-bit physical address should fit in a 4-byte entry size, right? And especially because we are not going to use all these bits, lower bits are going to be permission bits anyway, right? Yeah, so that's only relevant in that sense, right? So I want to kind of see that you understand that we are translating virtual address, right? So therefore the virtual address is relevant for us, right? So we have 29 bits of virtual address. Each page size is 11 bits, right? So therefore the page number is 18 bits. Page size is 2 to the power of 11, right? 2 kilobytes. So we have 18 bits for the page number. So this is what we need to translate. We need to translate 18 bits. We are not translating byte offset. We only translating page number. So to translate page number, we have to create a multi-level page table. So in each level, we have to have a page, right, which fits some entries. And each page is 2 to the power of 11, and each entry size is 2 to the power of 2. So therefore, in each level, we can fit 2 to the power of 9 entries. So 2 to the power of 9 multiplied by 2 to the power of 9, that's going to be 2 to the power of 18. So that means 2 levels are sufficient to translate this. Does that make sense? Again, physical address here is irrelevant, right? It can be like I could have just specified 33-bit, 31-bit. The answer would still be the same, right? But virtual address matters, right? So now let's say if I had 30-bit virtual address, how many levels would I need to have for 30-bit virtual address? Any ideas for 30-bit? Let's say I have instead of 29-bit virtual address, everything is still the same, but I have 30-bit virtual address. How many levels would I need to have? So if it's 30-bit, how many levels? Okay, go ahead.
It's still two,
Why?
because you have 19-bit virtual page number, which still is only 2 levels, 9 and an extra bit. What's the other?
Well, if you have 30-bit minus 11, that's going to be 19 bits, right?
Yeah.
But the page size still stays the same, entry size stays the same. So I can fit only 2 to the power of 9 in each level. So in 2 levels I can fit 18 bits, right? So then that means I have to have 3 levels, right? To fit the yeah. So even though I'm not gonna use the third level completely, right? I will just use maybe 1 entry from the third level, right? I still have to create a third level at that point, right? So it does make sense. So it doesn't necessarily have to be kind of equally dividable like this, right? So can potentially require you to not fully use the last level, right? So just make sure you calculate it correctly, right? Okay, go ahead.
So for the 30 bits, the breakdown will something look like 9 plus 9 plus 1,
Yes, yes.
wherein the last.
Yeah, last we are not using completely, we're just using you know, 1 entry, but we have to do that. Right? Well, we are using for last one, we use 2 entries, sorry. 2 to the power of 1 is 2, right? Yeah, so that's 2 entries that we use. But yeah, so but the point is we have to be able to accommodate this worst case scenario, right? Our worst case scenario, we need to translate the entire 18 bits. So and therefore, how many levels we need to have, we can calculate that, right? By just using that approach, right? So again, you have to show some sketch like this, at least like I put in the answer here. I mean, it's not as kind of expanded as this one, but it's still, I see that you do some calculation, right? So I guess the critical part, calculate how many entries you have in each page, how many bytes you have in the virtual page number, sorry, bits in the virtual page number, and then the final step, how many levels you will need to have, right, to accommodate this.
Quick follow-up question on that. What if we have a 28-bit virtual address? So
Then it's going to be 2 levels, right?
again, but we'll not be having both the entries as 9, 9, right?
Yeah, so it's going to be 9 and 8, right?
9 and 8.
Yeah, so we are not going to use the last, so the first level completely, right? So yeah, we will use 256 out of 512 entries, right? Okay, any other questions? Okay. So just this is again, I think we looked briefly in the past to this question already. I just want to make sure you fully understand this, right? And it's not difficult, but I guess this is where you can expect some calculations, right? Maybe there is another question, there is some calculations, but you know, again, it's not, it doesn't require a calculator, right? But if you want to bring a calculator, that's fine. Yeah, so I mean, if you have a calculator, bring it, so just you feel safe, right? So in case if you need to do some calculations. Okay, so let's look at today's lecture. So by the way, any questions about this so far? Okay, go ahead.
Question number 8, I think.
Question number 8, okay.
Question 4, sorry. Question 4.
Question 4. So this one, I think we looked in the background quiz, right, previously.
Yeah, the background quiz, but I just had one doubt. Over here, you said void pointer is 8. That's only in 64-bit, right? So we
Yes.
consider everything as 64-bit if we make the calculations.
Yeah, so that will be clarified in the midterm exam, right? So yeah, if I don't specify that it's 8 bytes, right? But in this example, I didn't specify that. But in the midterm, I believe it's specified, right? So will say that, so you don't need to assume anything, right? So it will say that the size of the pointer is this and this, right? If there is some question like that. So, but yeah, so but do you have any specific question? Okay. Okay. So let's look at some project 2 related information. There is the reason why I want to cover this now is because it's going to be also about page tables, and I feel like it may help you for your midterm preparation, right? Even though it's for project 2, you have some time, but I feel like we can look at this today so that it helps you for the midterm. So again, it's not something that there is some extra information, of course, here that will not be in the midterm, but at least to kind of recap whatever we covered about page tables that can help you. Yeah, so so let's look at the so now we'll look at some specific examples. So project 2 will be related to page tables, right? So in the page table setup, and you will have to set up a page table for real architecture, right? So like such as x86 64. So previously we looked at some general information, how page tables are set. We looked at some bits, permission bits, but now we'll look at some specific example, how it's implemented in a real architecture. And that's what's going to be also useful for your project, right? So before we get started, so we kind of learned that in addition to virtual page number to physical page number translation, which what the main purpose of the page table is, right? We also store some additional information such as valid bit, permission bit, like kernel user bit. So that means we call it supervisor bit. So there is also certain bits like reference bit. Remember, reference bit is something that whenever we reference a page table, whenever we reference a page, whether it's a read or write access, we will mark this bit. So that will be useful for some page replacement algorithms. But there is yet another bit. It's called a dirty bit. And dirty bit is basically somewhat different, right? So dirty bit is only set when you modify the page, not when you read, but when you modify. So unlike reference bit, which is both reading or writing any access, right? Dirty bit is only when you are writing. So what is the benefit of this? So why do we need this bit? Okay, go ahead.
So that we know if we replace it, like if we remove it from the cache, if we need to write it back to the disk.
So if you remove it from physical memory, right? Yeah. So if you need to write it to the disk, yes. So that's correct. Yeah. So we want to make sure that the page was modified, right? So because we don't want to write a page which has not been modified. So that's why we need this dirty bit, right? I mean, that's not to say that you cannot use it for something else, including maybe page replacement algorithms, but at least that's one of the straightforward examples of using the dirty bit. So you want to make sure that you don't want to write it to the disk carrier. So now the second question I have, we talked about page numbers, right? So obviously they have to in multi-level page table, and every level have to have page number, because you know it just points to the previous level, and only the leaf level points to the actual page number, right? But what about permission bits? So do we have them in the last level, first level, or in every level? So what about permission bits? Because typically aside from page number, we also store this permission bits. So where do we store those permission bits? Okay. Well, yes, I guess the answer here is a little bit trickier, right? So on the one hand, I should say that in general, you keep permission bits everywhere, right? So first of all, it depends on the architecture on every level, right? So you will fundamentally, you have some permission bits everywhere. And it's kind of important. Sometimes you have a parent bit which disables, like supersedes whatever you have child, right? Permissions there. So we mark the entire thing as only accessible from user mode. Only accessible from kernel mode. I'm sorry, right? So that means you can just mark one bit at the parent level, and that's it, right? Or you can have a specific, more fine-grained control in child. Maybe overall you don't have any restrictions, but then in the child level you decide that this specific page has that restriction, right? So I guess it goes with the most restrictive settings, right? Whether it's a parent or child. So, but parent is kind of naturally will kind of supersede the child, right? Whatever. If the parent is more restrictive, then we have to go with more restrictive rules. But if the child is more restrictive than parent, then we of course we have to go with the rule that defines in the child. So whatever is more restrictive, right? So we have to go with that. So yeah, so that's the general rule. Of course, we don't have bits on every level. Like some bits are present on that some levels, and we'll look at example in x86-64. So there is no definite answer here, but in general, we will have permission bits in every level. But there is some details, some nuances where some bits are only available at certain levels, right? So let's look in x86-64. This is an architecture that you will use for the translation, for the setting up of the page table. And we will use the actual architecture, right? So we will not use any kind of imaginary page table. We'll use the real page table, right, on the real architecture. So you can see that here we have a 4 kilobyte pages. So that means 12 bits. 2 to the power of 12 is 4 kilobyte. From 0 to 11, we have physical page offset in the virtual page address. In the virtual address, we have this lower 12 bits for the page for the byte offset. Then we have fancy names for 4 levels, effectively. It goes from 12 to 47 bit. So it's called page table entry, page directory table, page directory pointer table, page map level 4 table, right? So those are just fancy names for 4 levels, right, of the page table that we have. So the leaf level is what they call page table, right? That's the leaf level, the final level. And 4th level is actually the top level. So it's the opposite of what we looked at. Again, it's fine, whatever convention you use, whether you, as long as you clearly specify the top level is like level 4, or top level is level 1, it's up, like whatever convention you use, right? So, yeah, so we have these 4 levels. So in each, so let's look at one, let's just keep that for a moment, because that's something that looks familiar on what we looked for before. But then there is also some portion called sign extent, 48 to 63 bit. So this is something we haven't seen before. And this is specific to x86-64. So what is sign extent? Like in terms of integers? Any ideas? Okay, go ahead.
Extending the leftmost bit.
The uppermost bit, right, is propagated, right? So we take the 47 bit and copy it from 48 to 63. That's going to be exact copy. So sign extent is like when we, let's say, extend a negative number or positive number, like something that is signed integer, let's say 48-bit integer or 32-bit signed integer, right? We want to propagate to 64-bit signed integer, right? So we just copy that last bit. So if it was minus sign, then it will still remain minus sign, right? So that's the idea, right? So now, why would like all of a sudden we have that sign bit here? We like addresses are not really negative or positive, right? And it's kind of a little bit weird that we have negative addresses and positive addresses, right? So typical addresses are unsigned integers. So why does they still use signed integers? Well, of course, I don't know the exact reason, but at least I can explain what my understanding of why they do that, right? Of course, the exact reason can be something in addition to this. It's maybe not the only reason why they do that. But generally speaking, what we have is in x86-64, we have the vast majority of instructions that have a 32-bit constant, like constant 32-bit. Again, just an example, not something that you have to write down, but just an example, right? But if you want to write down, you can write down. That's fine. So a 32-bit constant, this is just an instruction, right? We'll move to a register. And the vast majority of instructions are moving 32-bit constant. So some instruction, only one instruction, I think, can move a 64-bit constant. So why is that the case? Well, if you move 64-bit constant, then our instruction will be too big, right? So it's going to create a lot of overhead. So most of the time, we want to deal with 32-bit constant, so that the instruction size is still reasonable, like 4 bytes plus something, right? Plus maybe 1 byte for the instruction. So it's still maybe 2 bytes for the instruction. So it's still reasonable, because if it's 8 bytes for the address plus this, that your code becomes very big, and that's really bad, right? So you want to keep it reasonable. So what they do, they extend a 32-bit constant to 64-bit constant. So they will take it to sign extended. So typically that works because you are dealing with some, numbers, either from maybe from 0 to 2 billion or whatever, right? To the power yeah. So let me put 2 billion approximately, right? Or maybe you deal with negative, right? Like you go to minus 2 billion, right? Approximately, right? So you are dealing with these numbers, right? So it's not such a, so you're typically not dealing with something larger than this, right? And that makes sense, right? To have that kind of restriction, because most of the time it will work, and in some exception when it doesn't work, you have that special instruction, but that takes takes more time and more space, right? So the same is sort of for addresses, right? So you have in fact you have 64-bit addresses, but you're not using the entire 64 bits. You only use 48 bits of these addresses. So it goes from 0 to 2 to the power 47, maybe minus 1 for the user space. That's kind of user space. And maybe you have kernel space in the bottom. That's going to be 2 to the power 64 minus 2 to the power 47. I think I'm correct here. And then up to 264 minus 1, right? So that's like the bottom. So that's the largest addresses. This is the smallest address, and this largest address. And in between, you have some big gap, right? So you have a big gap because you are not even using entire 64-bit addresses. You're only using 48-bit addresses. So half of this you dedicated for the user, half of for the kernel. So 2 to the power 47 addresses for the user, 2 to the power 47 addresses for the kernel, and everything in between is just a big gap. So now, in the future, they may kind of potentially extend it, and they actually did it. I think with 57-bit addresses. So it can potentially expand the user area a little bit further and kernel area a little bit further, right? And potentially they can go up to 64-bit in the future, and then they will meet, right? But right now I think it goes to 57 bits in the most recent extension. And you know, the common architectures and something that we'll use is going to be even less, 48 bit. And this is what this example, right? So this otherwise there's some gap there, right? So by sign extending, we can kind of create this model where we have low addresses here, and high addresses here, right? So and then there is a big gap in between. So the gap is actually going to be much bigger than the user and kernel space, because remember we only use 2 to the power 40, we only use 48 bits out of 64 bits, right? That means the vast majority of addresses we are not using. So we are only using 2 to the power 48 out of 2 to the power 64, right? So the gap should be pretty big if you draw it. I just draw it for illustration, but I guess user and kernel is going to be tiny if I draw this gap correctly, right? Yeah, so this is something to keep in mind. So these addresses are not valid. Something in between. So only addresses here and here are valid. And this is also what they call canonical address, I think in the manual, something like this. So something that would conform to the sign extended form, right? So why would you want to do that? Well, as I said, this is sign extended constant, right? So you can kind of run a user program maybe from 0 to like 2 gigabytes, right? So your program will not kind of exceed, like executable image typically will not exceed 2 gigabytes. So you will be able to use the most instructions like this, because that will correspond to the addresses in your user space. And maybe upper bits, right? So like from 2 to the power 32 to 2 to the power 47, you will use for the heap and stack. That don't require any constants, so you can use that for heap and stack. But for whatever requires the constant, like your code and data, they can lie in the first 2 gigabytes, right? So that will still work with this instruction. And the same for kernel, it can lie like the last 2 gigabytes of the kernel. That will still work with this constant, sign extended constant. So again, you will typically not have the kernel image that exceeds 2 gigabytes, right? So code data for modules and kernel should fit, and most constants should also fit in that range. Again, you can have heap and stack for the kernel line elsewhere, but constants are typically used for code and data. So this is where you need specific addresses and specific offsets, which are not variables, right? So yeah, so that's just the rationale for this, just to give you an idea. So remember, there is some gap in between, right? So it's really, you have some addresses here and some addresses here, but in between there is a big gap. So that's important when you consider level 4, because in level 4, it turns out that in level 4, the upper level, right? So it really kind of consists of 2 pieces. So level 4 consists effectively of 2 pieces. One piece corresponds to upper to the power 47, right? Another piece to the 247, right? To power 47. So it's really like goes literally like 255 entry, right? And 256. There is a big jump here between 255 and 256. Like there's a gap, right? So in terms of addresses. So up to this point, it goes normally, right? It's kind of goes as you expect, like this. And then there is a big jump between 255 and 256 because you're skipping this gap, and then there's finally the remaining portion, right? after this, right? So just keep that in mind. So level 4 is kind of an exception here. So all other levels are fine, but because of the sign extension, level 4 is kind of effectively split into two parts, right? And there is the gap, of course, you don't map anyhow, right? So let's look at this. Now let's look at the levels. So you can see that we have 48-bit address. If you put the sign extension aside, again, this is just an implementation detail. This is just relevant for x86-64. Again, not something that we will see in the midterm, right? But you know, it's just something that you have to be aware for the project, right? That you have the sign extension. You know, other architectures may decide to do different things, but that's what x86-64 decided to do. So we effectively have only 48 bits here, from 0 to 47. Those are the real thing that gives us some information, right? So out of this, 12 bits are used for the byte offset, and then you have full levels and 9 bits each. So why is it 9 bits each? So again, like looking at the previous example, we have 4 kilobyte pages, right? So divided by 8 byte entries, so 2 to the power 3. So 2 to the power 12 divided by 2 to the power 3 is going to be 2 to the power 9. So that means we have 512 entries in each level here, or 9 bits. So you can see that 9 bits for each level. So you have 9 plus 9 plus 9 plus 9 plus 12, right? So that's going to be 48-bit address. So, and again, the top level you load to a special register. That's just, you know, the top level. That I think we looked at this last time already when we talked about multi-level page tables. So you only specify the top level. So this is just specific example how we implement it, right? So let's look at the. Does anyone have any questions so far? So again, like remember, this is just one, like how you like in the x86-64, it's how you calculate how many levels you need, right? You need to accommodate 48-bit addresses, right? So let's actually look at this 48-bit addresses. You have 8 byte entries and 12-bit, like 2 to the power 12 bit, 2 to the power 12 bytes a page size, right? So you have 2 to the power 12 divided by 2 to the power 3 to the power of 9, 512 entries in each level, right? So that's going to be an 48-bit address. So 48 minus 12, you have to accommodate how many bits? You have to have 36 virtual page number, right? That you need to translate. So that's going to be what? 9 plus 9, right? So that's going to be, yeah, so I'm correct, right? 9 plus 9 plus 9, right? So that's going to be 36, right? So again, this is why we need 4 levels, right? So does make sense? So I mean, this is already given, but I could have. Okay, good.
Why not use 5 of it?
I'm sorry.
You have enough bits to use 5 of it.
Why do I not use 5 levels?
Yeah, but the sign extend, there's more than 9 bits for the sign extend.
Yes.
Add an extra page row.
Well, this doesn't give us any useful information. Sign extend is just repetition of the 47 bits, right?
Yeah.
So that's kind of corresponds to the gap that we have. We are not mapping that area, right? So it's just to conform. So we have to sign extend so that addresses. So I mean, the alternative would be user and kernel appear right after another. You just use 48 bits and nothing else, right? You just use 48 out of 64 bits. That would be the alternative. So you would have user, kernel, and then a big gap after this. That would be an alternative, like big gap after this, right? So they decided to do it differently. You have user, gap, and then you have kernel, right? So that would be correspond to 0 extent. And that would correspond to sign extent, right? So it's fundamentally, we still have 48-bit addresses, right? It's just how we spread out these portions, right? This is going to go 0 extension, this is sign extension. Does make sense? So fundamentally, signed bits is just additional thing that x86-64 has to do to correctly distribute these addresses, right? But we are mapping 48-bit address. And 48-bit address contains 12-bit byte offset. And that means we have to translate virtual page number, which is 36-bit. And for that, we need 4 levels, right? We need, in each level, we have 9 bits. Right, so yeah, so this is how we translate. Now, with more recent extension, they support 5-level page table. So they have used some portion of signed bits for the 5th level. So they have reduced the sign extended part, right? They still have it, but they have reduced it. So now they have the 5th level. But obviously, the more levels that you have, then the more expensive your hardware becomes, because you have to maintain TLB, which is, have to support that translation of already 4 levels or 5 levels. I mean, and imagine if you have a TLB miss, you have to go and retrieve every level, right? So that becomes really expensive. So you don't want to unnecessarily create too many levels. Does it make sense? Okay, so now how do we actually use these bits in each in each page table in each page table entry, right? So remember that for x86-64 they have chosen to use like 8-byte entries. That means we have bits from 0 to 63. So like first of all, from bits 12 to 51, that is the actual physical address, right? So when we look at the 4th level, we are obviously talking about the physical address of the 3rd level. When we look at the 3rd level, we are talking about physical level of the 2nd level and so on, right? Until we reach the final level where we are talking about the physical page number that we are mapping, right? So you have this from 12 to 51. That's kind of clear, right? So that's the address. So because they decided that they will only support 52-bit physical addresses. Again, has nothing to do like so 64-bit processor doesn't mean that they have to support 64-bit physical addresses. Doesn't mean that they have to support 64-bit virtual addresses. All that means that that we have to have for 64-bit, we're using probably 64-bit pointers, and pointers have to accommodate virtual addresses. So that means currently we have 48 bits. Tomorrow they may extend it like, I mean, they already extended it like to 57 bits, right? So they may further extend it to up to 64-bit potentially. But as long as we fit it in 64-bit word, we should be fine, right? Even if it's just 48-bit. So virtual address and physical address, they can be completely different. One can be larger than the other, or the other can be larger. I mean, I have on my machine, I think 48-bit virtual address and 39 physical address. So it's actually less physical address is even less than architectural supported. So architectural supported 52, but they're not actually implementing all 52 bits on my particular motherboard, right? On the computer. So therefore, it's also just a limit, right? So it says this is architectural limit. A given implementation may support fewer bits. It even says that explicitly in documentation, right? So, but up to 52 bits, that can be your physical address. So lower bits from 0 to 11 are used for permission bits. It's very similar to what we have in malloc, right? Where we had to recycle, when we were able to recycle some lower bits because of the alignment for like free unallocated status and so on. Here, the same idea. We don't need to know the byte offset because when we are mapping the entire pages, so obviously we can recycle lower 12 bits for something else. And they also use some upper bits because as I said, they're not going to 64-bit physical addresses, so they only support 52-bit physical address. So they can also, they reserve some upper bits. Like there is one already used non-executable bit, but there is some other bits available, right? For the future use. So you have some bits in the lower bits and some bits in the high bits in this case, right? And a base address, like the physical address, is from 12 to 51. So that's the last level. You can see there is permission bits here. Present bit is the valid bit that we covered previously. It's just a different name in x86-64, right? A read writable is like read only bit. That's we also covered in the past. User supervisor, supervisor bit. We have looked at this also, right? That's an access or reference bit. So that means the page has been referenced. And there is some other bits. We will not necessarily need to talk about this, but just, if you're curious, you can read about it. So the next level, pretty much the same idea. Some bits are not available, but overall there's similar permission bits. The second level is the same deal, right? So you have some bits, present bit is still there. And the final level, the leaf level, right? So here you can see that you have all these bits, right? So you have present bit, finally have D bit. This is dirty bit. So which previous levels didn't have. So previous level had access bit, present bit, supervisor bit, everything like this level has. But the last level also has this dirty bit. So that's different. So I guess it matters. The dirty bit only matters for a specific page. So it doesn't make sense to mark the parents, right? So therefore, they only implement the leaf level. So as I said, permission bits we have on every level, but there are some exceptions. And this is one of these exceptions. So also upper bits are used for something else. So available means you have to set it to 0. So available means reserved for the future use. So make sure whenever you initialize the page table and page table entries, you initialize every single bit, right? So you don't, if it's not used, it doesn't mean that you can skip it. You still have to initialize it to 0. Because otherwise CPU may see some arbitrary value, which can happen to be 1, and it'll say, oh, I don't support that feature. This is reserved for future use. So it's supposed to be 0 by default. So that can crash, so your program will crash in the best case scenario. And the worst case scenario will be some intermittent failure, which sometimes it crashes, sometimes it doesn't, depending on what values you got. So you have to initialize everything always. So be careful when you implement project 2 to make sure you initialize every single bit. So how can you define, just to wrap up our lecture, just let's look at one last thing. How do you define the page table entries? So you can have a bit field. So a bit field is just the way in C to to have to split the 64-bit integer or 8-byte entry, right, into multiple bits, right? So you can kind of split it individual structure. This is not a real struct, it's just 64-bit integer splits into fields, right? And then you can use individual bits and initialize it separately. It's just for illustration purposes. So the compiler will internally generate some mask like AND and OR mask, whatever is needed, right, to set these bits up, right? So you can use a bit field for that purpose. So I'm actually not recommending you to do that because it's easier to make a mistake when you use bit fields. You may forget to initialize some bit or some range of bits, or you may be a little bit off by some bits, right? So it's very easy to make a mistake if you are not careful, right? So you can use initialization based on like a regular masking, right? Or and bitwise mask, right? Just like you do for the malloc lab right now. So it may be more preferable, but it's up to you. So we have present bit, we have read writable, user mode bit. Then you can see the page address is 40 bits because we're not using lower 12 bits. This is reserved for permission bits. So we have 40-bit physical page number. So it's 40-bit physical page number and 36 virtual page number, right? So like we looked, 36 was the virtual page number, right? But the physical page number is 40-bit. Yeah, and some other bits. So make sure you initialize all of them. So that's how you can initialize just like regular struct members, right? You can initialize them separately. And finally, like let's look at an example how you would initialize 4 GB. So let's say you use this 48-bit virtual address mapping, right? And you want to initialize only 4 GB. So for 4 GB, how many entries do we need? So we have 4 kilobyte pages. And we need to map 4 GB. So we need 1 million pages. So 1 million entries. So we are mapping 1 million pages, right? Approximately. I mean, you can calculate the precise number, but I put it on the slides, but it's approximately 1 million. So 1 million pages that you map at the last level, that means that's the number of entries you have. In the last level, you have each page can accommodate of the last level 512 entries. So if you divide this 1 million by 512, you get 2048, right? That means that the preceding level has to contain 2048 entries. So, and that means each, again, on the preceding level, have 512 entries in each page. So that means you have 4 pages in the preceding level. So in the final level 3, you have to refer to the 4 pages from the previous level. That can fit to just one, page, because we only use 4 out of 512 entries at this point. And then the final level, we also just need 1 entry because that's just level 3 is just 1 page. So this is how we can create this mapping, right? So yes, we can go in more detail later, maybe next lecture, but the idea is that at each level, you kind of reducing the number. In the last level, we are not using all entries. We are only using some entries, right? So we are only just use 1 entry to the level 3. Level 3 is only going to use 4 entries. And final level 2 and level 1, we're going to be fully filled out, right? With entries. So in the last leaf level, you can see that the page numbers specify 0, 1, 2, 3, and up to 1 million, right? That's an absolute address of the pages that we want to map. We want to create, let's say, 1-to-1 mapping, virtual to physical mapping. Then in this case, that's going to be exactly the same page number, right? Just like the index counter, because it's 1-to-1 mapping. In the previous level, you will refer to the previous page, right? So that previous level page. So that means it's not longer the actual physical page number, but the physical address of the previous level page, right? Which keeps the entries. So this is why we're shifting by 12. So let's look at this example in more detail next time.